The 310.17 free air table in the National Electrical Code, or NEC, provides ampacity values for conductors installed in free air, assuming an ambient temperature of 30 degrees Celsius, which is equivalent to 86 degrees Fahrenheit. To determine if you can utilize the 310.17 free air table for conductors within a control enclosure, several factors must be considered. The description mentions a control enclosure with dimensions of 84 inches high, 154 inches long, and 24 inches deep, located in a climate-controlled electrical room, and equipped with circulating air. Firstly, consider the ambient temperature inside the enclosure. The climate-controlled environment implies that the temperature is maintained within a specific range. If the ambient temperature inside the enclosure remains at or below 30 degrees Celsius, the 310.17 free air table can be directly applied to determine the conductor ampacity. However, if the ambient temperature within the enclosure exceeds 30 degrees Celsius, it becomes necessary to apply temperature correction factors as outlined in NEC Article 310.15. These correction factors reduce the allowable ampacity of the conductors to account for the higher ambient temperature. Secondly, evaluate the impact of circulating air. The presence of circulating air inside the enclosure can significantly improve heat dissipation from the conductors. This enhanced heat dissipation may allow for a high conductor ampacity compared to a situation without circulating air. However, the effectiveness of the circulating air depends on several variables, including the airflow rate, the design of the enclosure, and the layout of the conductors. It is important to ensure that the circulating air is sufficient to maintain the conductor temperature within acceptable limits. Thirdly, NEC regulations must be followed. The NEC provides guidelines for conductor ampacity, installation methods, and safety requirements. When determining the appropriate ampacity for conductors in a control enclosure, it is crucial to adhere to all relevant NEC articles and sections. This includes considering factors such as conductor insulation type, termination temperature ratings, and enclosure dirting factors. In summary, the applicability of the 310.17 free air table for a control enclosure depends on the ambient temperature and the effectiveness of the circulating air. If the ambient temperature is at or below 30 degrees Celsius and the circulating air is adequate, the table can be used directly. If the ambient temperature exceeds 30 degrees Celsius, temperature correction factors must be applied. To accurately determine the appropriate ampacity of conductors in a control enclosure, it's recommended to consult with a qualified electrical engineer who can assess the specific conditions and ensure compliance with all applicable codes and standards. Factors affecting conductor ampacity also include conductor insulation type, such as THHN, THWN, or XHHW, each having different temperature ratings. The termination temperature ratings of the connected equipment, such as circuit breakers, disconnects, or other devices, must be considered. These devices typically have terminals rated for 60 degrees Celsius or 75 degrees Celsius. The conductor ampacity must be selected based on the lowest temperature rating of the conductor insulation and the termination points. If the equipment is only rated for 60 degrees Celsius, the ampacity of the conductor must be based on the 60 degrees Celsius column in the ampacity tables, even if the conductor is rated for a higher temperature. Enclosure dirting factors also play a role. If multiple current-carrying conductors are bundled together or installed in close proximity within an enclosure, the heat generated by the conductors can raise the ambient temperature inside the enclosure, and this requires ampacity dirting. NEC Article 310.15c provides guidance on ampacity dirting factors for multiple conductors in a raceway or cable. Similar dirting factors may apply to conductors in an enclosure, depending on the specific installation conditions. Practical considerations should also be taken into account. Proper conductor sizing is essential for safety and reliability. Undersized conductors can overheat, leading to insulation damage, premature failure, or even fire hazards. Oversized conductors, while not posing a safety risk, can be unnecessarily expensive. Conducting a load calculation to determine the actual current demand of the equipment served by the conductors is necessary. This load calculation should include all continuous and non-continuous loads, as well as any applicable demand factors. The conductor ampacity should be at least equal to the calculated load current, plus any applicable safety factors. Regular inspection and maintenance of the control enclosure is also helpful. Periodic inspections should be conducted to ensure that the circulating air system is functioning properly and that there are no signs of overheating or insulation damage. Any issues identified during inspection should be promptly addressed to prevent potential problems. Documentation of all calculations, conductor sizing decisions, and dirting factors should be kept for future reference and to demonstrate compliance with applicable codes and standards. This documentation can be helpful during inspections or audits. In addition to temperature and circulating air, altitude affects conductor ampacity. At higher altitudes, the air is less dense, which reduces the cooling effect of the surrounding air. NEC Table 310.15b2 provides correction factors for installations at altitudes above 3,000 feet. If the control enclosure is located at a high altitude, these correction factors should be applied to the conductor ampacity. Conductor bundling and spacing also matters. When conductors are bundled together or installed with minimal spacing, heat dissipation is reduced, leading to higher conductor temperatures. NEC Table 310.15 cone provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These adjustment factors should be applied when conductors are bundled together in the control enclosure. Voltage drop is also a relevant consideration. While voltage drop does not directly affect conductor ampacity, it can impact the performance of the equipment served by the conductors. NEC Informational Note number 1 to 210.19a and Informational Note number 1 to 215.2 A3 recommends that voltage drop should not exceed 3% for feeders and 5% for branch circuits. The conductor size may need to be increased to limit voltage drop to these values. Harmonics can also be important in some cases. In systems with significant harmonic currents, the neutral conductor may carry a substantial amount of current. NEC 220.61 cone requires that the neutral conductor be sized to carry the maximum unbalanced load, including harmonic currents. If the control enclosure serves equipment with nonlinear loads, such as variable frequency drives, the neutral conductor size should be carefully evaluated. Continuous versus non-continuous loads are also worth considering. NEC 210.19a requires that branch circuit conductors supplying continuous loads be sized to carry not less than 125% of the continuous load, plus the non-continuous load. A continuous load is defined as a load that operates for 3 hours or more at a time. If the control enclosure serves continuous loads, this requirement should be taken into account when sizing the conductors. Spare capacity is another factor that should be part of design. It is generally good practice to provide some spare capacity in the conductor sizing to accommodate future load growth. This can avoid the need to replace the conductors if the load increases in the future. The specific amount of spare capacity will depend on the anticipated future load and the cost of replacing the conductors. Using appropriate overcurrent protection is also vital. NEC 240.4 requires that conductors be protected against overcurrent in accordance with their ampacity. The overcurrent protection device, such as a circuit breaker or fuse, should be sized to protect the conductors from overload in short circuit conditions. The overcurrent protection device rating should not exceed the conductor ampacity unless permitted by specific exceptions in the NEC. The type of control enclosure will also have some effect. The type of control enclosure can affect the heat dissipation and the ambient temperature inside the enclosure. Enclosures are typically rated according to NEMA standards, such as NEMA 1, NEMA 3R, NEMA 4, or NEMA 12. Enclosures that are tightly sealed or located in hot environments may require additional ventilation or cooling to maintain the ambient temperature within acceptable limits. Installation practices also matter. Proper installation practices can help to ensure that conductors are adequately cooled and that voltage drop is minimized. Conductors should be installed in a neat and workmanlike manner with adequate spacing between conductors. Conductors should not be tightly bundled or routed through areas where they are likely to be exposed to excessive heat or mechanical damage. Documentation is also key. Maintaining accurate documentation of all conductor sizing calculations, derating factors, and installation details is critical for future reference and troubleshooting. This documentation should be readily available to maintenance personnel and should be updated whenever changes are made to the electrical system. Following industry best practices is always prudent. In addition to the NEC requirements, there are also industry best practices for conductor sizing and installation. These best practices may include using larger conductor sizes than required by the NEC, providing additional ventilation or cooling for enclosures, and using surge protection devices to protect conductors from voltage transients. Consulting with experienced electrical engineers and contractors can help to ensure that the conductors are sized and installed in accordance with industry best practices. Codes and standards updates also happen periodically. The NEC is updated every 3 years, and it is important to stay current with the latest requirements. Changes to the NEC can affect conductor sizing, derating factors, and installation requirements. Subscribing to industry publications and attending training courses can help to stay informed of the latest code changes. Safety considerations should never be ignored. Electrical safety should always be the top priority when working with conductors and control enclosures. Conductors should be properly insulated and protected from damage. Lockout/tagout procedures should be followed when working on de-energized circuits. Personal protective equipment, such as gloves, safety glasses, and arc flash protection should be used when working on energized circuits. The specific type of equipment being controlled within the enclosure also needs consideration. The type of equipment being controlled within the enclosure can affect the conductor sizing and installation requirements. For example, if the enclosure controls motors, the conductors must be sized to handle the motor starting current, which can be several times the motor's full load current. NEC 430 provides specific requirements for motor circuit conductors. Similarly, if the enclosure controls lighting, the conductors must be sized to handle the inrush current of the lighting fixtures. The operating environment is also relevant. The operating environment of the control enclosure can affect the conductor insulation type and the need for additional protection. If the enclosure is located in a corrosive environment, conductors with corrosion-resistant insulation should be used. If the enclosure is located in a hazardous location, such as a Class 1, Division 1 or Division 2 area, conductors and enclosures that are approved for use in hazardous locations must be used. The available fault current at the location of the control enclosure must also be calculated and considered. The available fault current is the maximum current that could flow in the event of a short circuit. The conductors and overcurrent protection devices must be rated to withstand the available fault current. If the available fault current is too high, current-limiting fuses or other protective devices may be required. Grounding and bonding are also very important. Proper grounding and bonding are essential for electrical safety and to minimize the risk of electric shock. The control enclosure and all metallic parts of the electrical system must be properly grounded and bonded in accordance with NEC Article 250. Grounding conductors should be sized in accordance with NEC Table 250.122. Surge protection is also a useful thing to look at. Surge protection devices can help to protect conductors and equipment from voltage transients caused by lightning strikes, switching surges, and other events. Surge protection devices should be installed at the service entrance and at the control enclosure to provide comprehensive surge protection. The cost of materials and labor should also be thought about. The cost of conductors, enclosures, and other electrical materials can vary significantly depending on the size, type, and quantity. It is important to consider the cost of materials and labor when designing and installing a control enclosure. Value engineering techniques can be used to optimize the design and minimize costs without compromising safety or reliability. Longevity and reliability is an important aspect. The expected lifespan and reliability of the electrical system should be considered when selecting conductors and equipment. Using high-quality materials and following industry best practices can help to ensure that the electrical system will provide many years of trouble-free service. Consider the need for future expansion of the control enclosure. If future expansion is anticipated, it is important to provide adequate space and spare capacity in the enclosure. This may include using a larger enclosure, installing additional conduit ones, and providing spare conductors. Detailed system design documents are a must. Prepare detailed system design documents, including single-line diagrams, wiring schematics, and panel schedules. These documents should be reviewed and approved by a qualified electrical engineer before construction begins. As-built drawings should be created after the project is completed to reflect any changes that were made during construction. Inspections and testing should be done. After the control enclosure is installed, it should be inspected and tested to ensure that it meets all applicable codes and standards. Testing should include insulation resistance testing, ground impedance testing, and functional testing of all equipment. Any deficiencies identified during testing should be corrected before the enclosure is put into service. Training and qualifications of personnel will matter. Ensure that all personnel who work on the control enclosure are properly trained and qualified. Electrical work should only be performed by licensed electricians or qualified electrical workers. Training should include electrical safety lockout/tagout procedures and proper use of personal protective equipment. A maintenance program is useful. Implement a regular maintenance program for the control enclosure. This program should include periodic inspections, cleaning, and testing. The maintenance program should be documented and followed to ensure that the enclosure is operating safely and reliably. Use of appropriate tools and equipment is also important. Use appropriate tools and equipment when working on the control enclosure. Use insulated tools when working on energized circuits. Use a voltage tester to verify that circuits are de-energized before working on them. Use a torque wrench to tighten connections to the proper torque. Consider energy efficiency. When designing and installing a control enclosure, consider energy efficiency. Use energy-efficient equipment and lighting. Install variable frequency drives to control motor speed. Use power monitoring systems to track energy consumption. Safety interlocks can be a good measure. Install safety interlocks on the control enclosure to prevent accidental contact with energized parts. Safety interlocks should be designed to automatically de-energize the equipment when the enclosure door is opened. Labeling should be in place and accurate. Label all conductors, equipment, and control devices in the enclosure. Labeling should be clear, concise, and durable. Labeling should comply with applicable codes and standards. Adhere to environmental regulations. Dispose of waste materials properly. Use environmentally friendly materials whenever possible. Comply with all applicable environmental regulations. Planning and communication between parties is necessary. Plan the control enclosure installation carefully. Communicate with all stakeholders to ensure that the installation is coordinated and that all requirements are met. Review the design and installation with a qualified electrical engineer before proceeding. Keep records organized and accessible. Maintain accurate records of the control enclosure design, installation, testing, and maintenance. Keep these records organized and accessible for future reference. Consider accessibility. Ensure that the control enclosure is easily accessible for maintenance and repair. Provide adequate clearance around the enclosure. Ensure that the enclosure door can be opened fully. Consider the risk of arc flash. Perform an arc flash hazard analysis to determine the potential arc flash hazard level at the control enclosure. Provide appropriate arc flash protection for personnel who work on the enclosure.